Okay, I think we're getting to the point where we've reached critical mass and we're ready to start. So first of all, thanks everyone for being here. I know that it's early, it's week number 2, and people might be starting to get tired, so I really appreciate you being here for this talk. So to begin, I just want to give a very brief overview on what we did yesterday, what are the things that we want to do today. So yesterday, we briefly introduced quantum machine learning. We discussed about some of the problems that might arise, like barren plateaus and classical simulability. And we kind of worked with this. I presented this example where we use Hamiltonian variational ansatz to prepare the ground states of a VQE molecule of an Ising model via VQE. And then we use the quantum convolutional neural network for simulations. And we saw that this is at least 3 papers. But the thing is that it turns out that all of the things that those quantum circuits are doing is fully classically simulable, as we will try to prove today and tomorrow. So today, I will mainly focus on some Lie algebraic simulation techniques for the transverse field Ising model. And to begin, let us set the framework again. We were working with this paradigm of quantum machine learning, where we said, OK, let's try to put some problem inside of a quantum computer. Let's try to use the learning methodology where we turn some problem of interest into an optimization task. We're going to try to train a parameterized quantum circuit, make measurements to estimate the value of some loss function, optimize those classically, and try to go around this loop over and over again. And something that is going to be important throughout this talk, and I'm going to mostly be working on the blackboard, so I'm going to start putting some stuff here, is that the loss function of interest, let me actually write it like this instead of theta, is going to take this form. And this is the kind of things that we want to try to show that classical computers can simulate and can obtain, and you don't need a quantum computer for those. As we saw, barren plateaus are a curse of dimensionality. We were a little bit concerned that we were doing this problem of slapping machine learning into quantum computing. And I think people now have the tools to understand what Z2 symmetric means. If you build the Cayley table for this meme, you will see that it is a representation of Z2. So I think now you have all the representation and group theoretical tools to understand this. Then once we saw that we had this curse of dimensionality problem, we realized that the way in which we're solving barren plateaus is by encoding the problem in a very small polynomially sized subspace, and that this subspace might be classically simulable. And I'm trying to do a recap via memes, is what I call this. So then we introduced these 2 computational models, and we said, maybe we don't really need this whole pipeline of going back and forth between the quantum and the classical. Maybe we can just do something that will look like this, where we can use a quantum computer for some initial data acquisition phase, and then we can estimate the loss function by feeding that initial data that we've acquired to a classical computer. And remember, the whole point is that you will only be allowed to use the quantum computer during an initial data acquisition phase. This will last polynomial time, and the measurement outcomes you need to store in a polynomially sized measurement. So you cannot do full state tomography or anything like that. And once this initial phase is over, you cannot access your quantum computer anymore. So what are the steps that we're going to be trying to follow? And this is going to be the recipe for both today and tomorrow. We will first try to identify what is the subspace of interest, the subspace where our barren plateau-free model lives. And the motto is we will always think about the Heisenberg evolution. We will determine what is the size of what is the type of measurements that we need to do in our initial state, or in our data set, so that we can represent our data in this subspace. And then we will study what is the class of simulability that we get. Because remember, we have different types. We have average type simulability for a landscape or solution-based. We will recall those in a second. And the 4th step for this is profit. You have now successfully dequantized a quantum algorithm. So very briefly, again, I want to recall these notions of simulability that we presented yesterday. We have simulability on average, where we just care about sampling some set of parameters or some unitary from our model. And this we can approximate with small precision epsilon with high probability. We might also want to have this for all the values of the landscape. And we might have this practical one That is, I want to find a solution with my simulated model that is as good as the one as I would get if I were to do the whole thing. So before we fully jump into this, let's do a warm-up example. Let's try to take this guy right here. It is Barron Plateau free and hardware efficient ansatz, or this architecture where 2 qubit gates act on neighboring pairs of qubits. And we said if you have shallow depth and local measurements, this doesn't have Barron Plateaus. So the first question is, what is the subspace of interest that we will try to simulate here? And this is open question for you all. Where do the relevant dynamics live here? And again, here's the tip. Always think about the Heisenberg evolution. Yes, it is a Pauli subspace, but which Pauli subspace? Is it like Pauli's on all the qubits? Is it Pauli's on all the qubits? So which two? You would say these two? These two are the qubits that you will measure. But the problem is that this evolution doesn't just happen in these 2 qubits. The evolution, if you take your measurement operator and you Heisenberg evolve it, you have more than these 2 qubits. You have all the qubits in the backward slide cone. So the things that we need to be able to estimate is we take some measurement here, we Heisenberg evolve it, now we're going to live on the set of operators that are acting on these 6 qubits. Do we all agree on this? Okay, so this is our subspace of interest. Now imagine that you have some input state here rho that you're going to be sending through this circuit. What is the type of measurements that I need to make on this state such that I can learn the action of this circuit a posteriori? Remember, you're not allowed to implement the circuit at this point. This is initial data acquisition phase. I will give you the initial state. This might be a set of states from a data set. And you need to perform some set of measurements, and then you're not allowed to use the quantum computer anymore. What type of measurements would you do? And it needs to be efficient. Let's assume that we have a single input state here, rho. So which qubits would you measure here? You would measure these 2? These 2. And I guess so again, remember that the idea is that you have this 1, 2, 1, 2, 3, 4, 5, 6, 1, 2. I'm going to try to not spend too much time drawing this, so I'm going to be very quick about this. So these are the qubits in our light cone, right? And the whole point is that we want to have a classical algorithm that will estimate that quantity right there for any set of parameters here. But you need to be able to do this by splitting this in half. Initially, during your initial data acquisition phase, you can make measurements on this state, and then it's going to be the classical computer that estimates the action of this circuit. So you said make measurements on these 2 first qubits and these 2 last qubits? Yeah. What would you do in them? Again, remember, you need to do measurements, and afterwards, I'm going to give you this circuit, a set of parameters, and you need to estimate the loss function. Yeah, that's perfectly fine. You could do full state tomography. You could just learn all of the probability distribution. You could learn all of this, all the Pauli observables. And why is this efficient? Because we said this has no Barron plateau if the depth is at most logarithmically scaling in the number of qubits. So if I have depth L, you can try to do this, and the number of qubits that you have is 2L inside of the light cone. So this is going to be order log n. What is the cost of doing full state tomography on an m qubit system? It is going to be at most 4 to the m, 2 to the n if it's pure state, 4 to the n m if it's mixed. Now we replace m with log n, because this is the number of qubits that we need to do full state tomography, and you can show that this is at most polynomially expensive. So in this case, you could just perfectly do full state tomography. You save that representation of the state, and then you simulate the action of the system. You might also say, okay, but maybe this is too expensive. I can just do classical shadows, because classical shadows will precisely be able to give you expectation value of local observables of up to log n bodiness. So this is exactly what you would do here. You would just take your initial state, you would do full state tomography, and then once I give you a new set of parameters, you just forget about the rest of the circuit because it's doing nothing, and you're acting on a polynomially sized subspace, right? Is there any issues with this? Okay, so in this case, what type of simulability do we get? Are you going to be able to simulate this on average for all parameters? Which type of simulability do you think you would get? If I give you now this state and a set of parameters, would you be able to estimate the loss function? Yeah, you can. So this would be a simulability where you can get this guy. This is our simulated. And this precision epsilon is actually the precision to which you're learning each one of your poly expectation values, which is actually going to come into play like this. So yeah, we can perfectly do this with polynomial precision for all parameters.
But this wouldn't be the case if there were no barren plateaus.
Yes, that has no barren plateaus.
Right, so we can estimate the loss function because there's no barren plateaus. What if there were barren plateaus? Would we still be able?
Actually, estimating the loss function landscape on a barren plateaus, in average, is trivially easy. Because with high probability, you pick a point in the landscape, and it's just the mean, say 0. So simulating a barren plateau on average, I just guess 0, and with exponentially high probability, I'm going to be correct. So yeah, in this case, what we're doing is for this sort of shallow circuit that doesn't have barren plateau, and you can actually see that it's trivial. It's shamefully trivial. And it took us way too long to realize this. But how do we go from here? We've already determined the class of simulation landscape, and that's it. Now you know that if you have shallow depth, harder efficient ansatz with local measurements, don't run this in a quantum computer. You really don't need to. You can just do a classical simulation with some easy and efficient tomographic procedure. So again, and the question now is, what is the target that we're going to be studying today? And we said we're going to be studying the simulation of Ising models with Hamiltonian variational ansatz. So we said that if you have a Hamiltonian that looks like this is what the circuit is going to look like. We can also say what happens if we build a Hamiltonian variational ansatz with an Ising model that has transverse and longitudinal magnetic field. So you're going to have these two right here. Now the ansatz is going to look like this. So you might be like, OK, I have this ansatz. Why don't I just add some extra gates to increase my expressiveness? Let me just put some rotations around the z gates like in there. This can't be too bad, right? Well, it turns out that this one doesn't have barren plateaus. This one does have barren plateaus. And we will try to understand why such a seemingly innocuous change in your landscape, in your ansatz, can so drastically change the behavior of your landscape. And with that, I think that's pretty much all that I wanted to show today. So it's time to do Blackboard. Even I feel ashamed to leave this up for 1 hour, up there just like a meme for 1 hour. So I kind of just build a cheat sheet that will leave up there so that you don't have to stare at the meme for a whole hour. All right. So who here has heard about dynamical Lie algebras of parameterized quantum circuits? Oh, okay, interesting. So let's try to explain this from the beginning. So I'm going to use this Blackboard right here to write the stuff that is not going to change throughout the whole lecture. So we're going to be considering parameterized quantum circuits that are going to take this form. So this is quite general. You're going to have a circuit that is composed by exponentiation of a given set of Hermitian operators. You're going to repeat some of those k times, and you might repeat this on a layered structure. If you don't have layered structure, just forget about this, and you will perfectly, your algorithm will perfectly work. So you don't need to have periodic structure. It's just that this is very common for variational algorithms. Now, one of the first questions that one can ask is, we've already seen that circuits that are too expressive are bound to have issues. They're bound to have barren plateaus. So a question that one might ask is, what is the ultimate expressiveness of this circuit? If you could do as many layers as you could and just change the parameters as much as you could, what is the breadth of unitaries that this circuit can produce? How do we quantify this? How do we understand what are all the possible set of unitaries that I can get from something that looks like here? And the thing is that this is very, there is a way to do this. Let me just define the set of generators as the set of these guys right here. Right? It's just the things that I'm going to be exponentiating in my circuit. And from here, I can define something that is called the dynamical Lie algebra. So how is this defined? This is curly G. And this, I'm going to write something, and you can let me know if this makes sense to you. This right here is called the Lie closure. People heard about this before. Or if I tell you, like, compute the Lie closure of this set of observables, does it make sense what that is? OK, so what you would do is, if I give you a set of operators, what you're going to do is you're going to start doing all the nested commutators. I'm going to do H1 commuting with H2, H1 commuting with H3, H1, and so on until I get from, oh, this should be K. Sorry, let me be consistent with my own notation. So in here, I would compute Hi, Hj for all Ij. I need to put an I here because I'm defining these as Q-Hermitian matrices. And this is going to give me a new set of operators. Now, I'm going to take this new set of operators, and I'm going to try to decompose it into the things that were already here. So I can write this as a summation of, I don't want to use F just yet. Let me do A, I, J, K with Hk, plus potentially some new operators that weren't in my original set. So I can have here something which looks like B, I, J, K. Let me call this H tilde K. And I've divided this in such a way that these are orthonormal. They have no overlap. So what you can see is that, OK, I commute these guys. I'm going to get stuff that was already in this set. And I should keep me honest here. I'm probably going to forget a lot of I's. I have stuff that was already in the set. So this, I don't care. But I have new stuff that is going to be generated. So now I take this new set of operators, I put them in a new set of generators, and I start repeating this process. Eventually, I'm not going to be able to generate any more stuff. And once you have a set of operators that is closed under commutation, that is a Lie algebra. Right? So by definition, we're trying to find what is the Lie algebra that is obtained from this set of generators. If you've seen the exercises that are online that I sent, there is a few examples of computing a few of those to try to see what is the set of operators that you can reach. And sometimes you're going to be able to get all the Paulis acting in your Hilbert space. Sometimes you're not going to be able to get all of them. But this is actually going to inform you about what is the set of unitaries that you can get. Is this too abstract, or is this OK? We could also try to do an explicit example. The problem is that the minimal example is in the hackathon, so we would have to go to something that is a little bit less trivial. But I can actually give you one. I can give you the solution. So let's think about the HVA on 2 qubits for Ising model. So we would have our set of generators is Z1, Z2, X1, x2, because we saw that our circuit was composed of Z rotations and then entangling XX gates, right? And you just repeat this a bunch of times. So this is your set of generators. So if you do the Lie closure of this set right here, let's call it transverse field Ising model, you are going to realize that you're not able to generate all 16 Paulis on 2 qubits. And I can give you the solution, because it's actually fairly easy to write. This is going to be, this is a Lie algebra, so of course, you can do linear combination of these things. So I allow combination with respect to real numbers. But I'm going to have here Z1, Z2, X1, X2. Of course, this was the starting set. I will also get Y1, Y2, X1, Y1, X2, X1, Y2. And that's it. That is all the operators that I can generate by doing nested commutators of these things. I cannot generate anything else. So you can see that the fact that I'm not generating all 16 operators already tells me that this is not as expressive as it could possibly be. On the other hand, if you do the longitudinal transverse field Ising model, where your set of generators also contains this, I think it was X gates. So your set of generators is going to be Z1, Z2, X1, X2, X1, X2. And you do the Lie closure of this guy right here. You will see that you will get all 16 Paulis. So this tells me that this is isomorphic to SU4, which is as expressive as you could possibly be. And of course, the importance of this Lie algebra is that we can now answer the question of how do we quantify all the unitaries that could ever be created. We know that for all L and for all sets of parameters, we're going to have that this unitary belongs to the Lie group obtained by exponentiation of this Lie algebra. So this is the key point of why the Lie algebra is important, because it will allow us to find what is the group that ultimately characterizes all the unitaries that I'm going to be able to prepare. Now, if it's not obvious why nested commutators come into play, you can always remember the BCH formula, which tells you if I have e to the a times e to the b, and I want to write this as e to the c, you know that this can be expressed in terms of a plus b. I have my own cheat sheet here because there's stuff that I will absolutely never remember. This formula is one of them. And here you have all higher order nested commutators. So let's think about this. What happens if we take that formula and we apply it to this equation right here? We start with 2 unitaries. We combine them into one. Now we get the exponential of something that is nested commutators. Then we take the third unitary. We again do the same. You're going to get all the nested commutators of C and the next one. And you just keep doing this. And eventually, this thing is going to converge. It's an infinitely large summation. But the number of distinct operators that you can generate needs to be finite. And it needs to be finite because, at most, it can be all the Pauli operators. And note that I'm putting an S here because I'm never going to be able to generate the identity, right? If I start with Hermitian operators, there's no way that I can get an identity by commuting them. So this is a little bit the intuition of why the dynamical Lie algebra, in a way, captures what is the expressiveness of the circuit through trying to take this equation and compress it into a single exponential. OK, I hope dynamical Lie algebra is clear, because now that we have this, and if you remember what it is that we said yesterday, once we have a group and once we have a vector space, we can start thinking about how this group decomposes into irreps of our vector space. So we have our group G. Let me call this the dynamical Lie group. And of course, I should be more precise. I should say that where these operators live, I'm going to be working with an n-qubit Hilbert space, H, which is C2 tensor n. And these guys, rho and O, they belong to the set of bounded operators acting on this Hilbert space. And I think that now we've defined things a little bit more formally. So I can now ask the question, what is the group that we have? We already know it's a dynamical Lie group. But what was our ultimate goal? And this is something that I want you to always keep in mind, which was some of the, oh, I didn't put the rules here. But we said our ultimate goal is to simulate this action. And we said what we need to do is we need to think about the Heisenberg evolution of the measurement operator, because ultimately what we want to try to answer is, given this guy right here, where can this go? In which part of operator space does this Heisenberg evolve operator live? Can it spread all over the place? Or maybe it's just contained in a small subspace, right? And we've already said, okay, this is a unitary. We know the group that it belongs to. We know the vector space that we're interested in. And we've already said that EREPs are invariant subspaces. It tells us about subspaces that are preserved under the action of my group. So this is exactly what we're looking for. So now I can just say, okay, let me define this representation. And I'm being here a little bit vague in the sense that this is a representation of a group. So if we want it to be a little bit more formal, I should write an R here because G is an abstract algebra, and this is a representation of an algebra. And this is a representation of a group. So from here onwards, G, big G and small g are going to be abstract objects, and this R is the representation that we're working with. So now I can define a different representation, which let me just call like adjoint action, which is going to give me, is going to take an element of the group, and is going to give me a linear map acting on BH. And I'm going to be more explicit, and I'm going to define its action over an operator as conjugation. So this would be acting on O. How do I want to do this? So it's the adjoint action, right? You act via conjugation on operators, because this is what we're interested in. And now we can ask the question, under this representation, which is acting on this vector space, how will this guy decompose? And we know that the most general answer is that this, which I'm denoting in this way, is going to decompose into invariant subspaces or irreducible representations. Now here, I'm being a little bit informal, in which this contains the index that labels multiplicity and also the EREP, but this is a little bit simple to work with. That way we don't have to keep track of multiplicities. So we know that this has to exist, because this is what representation theory tells us. You give me a group, you give me a representation, you give me a vector space, I'll tell you how this guy decomposes. But now, this is extremely great, because now we know that if O belongs to one of those, then I don't need to study the action of the unitary over the whole space. I just need to study the action of the unitary over this subspace right here, which is the second step. We said, first, identify the subspace that you're living in. We've kind of already done this here. We use rep theory to get these guys. Then we just take our measurement operator, and we just see which one or which ones it belongs to. Let me just assume now that it belongs to one, but this can be generalized whenever it's spread over many. So we've already identified the subspace. Now we need to see the action of the unitary in this subspace. And again, remember, this is always going to be the same set of steps that we're going to be following. So we just need to represent how U acts here. And up to this point, I'm going to be very abstract, but we're going to go to some examples afterwards. So how do we go about doing that? We have a problem where we have a Lie group, and we want to learn something about a Lie group. We want to know how the Lie group acts here. But if you remember, the second tip is that if you have a problem at the Lie group level, the recommendation is always go to the Lie algebra level, solve it there, and then come back to the Lie group. So let's try to see if we can understand this. So what we have is, and this is a nice result from representation theory, is that if you have an adjoint action of the Lie group, this induces, via the exponential map, an adjoint small ad representation of the Lie group, which is given by this. So when this acts on O, this is just G commuting with O. So if unitaries act via conjugation, the elements of the Lie algebra act via commutation. The easiest way to see this equivalence, if you want to try to prove it, is just write this unitary as e to the a, where a belongs to the algebra, which we already know it should be possible because of this equation right here. And take the derivative and put here a parameter theta. Take the derivative of this with respect to theta and evaluate infinitesimally. And you will see that to first order, you're going to get this commutator right here. So unitaries act via conjugation, algebra acts via commutation. So now we already know that we said we want to study how unitary acts via conjugation in this irrep. Well, we can study how the algebra acts via commutation in this irrep. I hope that made sense. Okay, so now let me define as p lambda mu, when mu goes from 1 to the dimension of b lambda, as a orthonormal basis for this subspace, which I can always do. It's a subspace, it's a vector space. I can always find an orthonormal basis. So what we're going to try to compute now is some stuff that is called the structure constants. And these are simply defined, and let me actually, yes, this is Hermitian. So this is something that is important, because now I want to compute stuff that looks like this. I, H, K, I, P mu, lambda. I want to compute these nested commutators. And it's not hard to see that because these guys are closed under this action, so if I conjugate an operator, I stay in here because it's an invariant subspace. If I commute, I have to stay here. So that necessarily implies that this can be written in this form. P mu lambda, which is just telling me I take something in the irrep, I commute it, I stay in the irrep. This is a necessary condition from the fact that it's an invariant subspace. So now, this is actually really, really, really great, because this will allow us to define the small adjoint. It's unfortunate that I've already defined an adjoint representation here, because I'm going to define a second one. Let me call this adjoint. I should call this adjoint action, and this is going to be the adjoint representation. So what is the adjoint representation? First, it's a representation, so it's a map. Let me denote it like this, because now it's just small ad. It's just going to be acting on this lambda. And what it's going to do is that it is going to take an element in the algebra, and is going to return a matrix that is dimension of b lambda times dimension of b lambda, which is great because we've went from objects that operate in an exponentially large space to objects that are now simply dimension of b lambda times dimension of b lambda. And of course, I need to define this guy. So what I'm going to do is I'm going to define it for an element like this, where its mu newth entrance is simply f mu nu k. So it's this guy right here. And you can always think about this as this. If you need to actually compute it, you can always do it in this way. Because I've assumed that this is an orthonormal basis, right? So this is great, and you can actually prove that this is a group this is an algebra homomorphism. It will respect all of your commutation rules. And why do we like this? Because once we've defined a representation of the algebra level, just like representations at the group level induce representations at the algebra level, the converse is also true. If I define a representation at the algebra level, I can always take it to be a representation at the group level. So now, let me define the big adjoint representation. So now this is for the group. Let me call this phi, big add acting on lemma, that takes an element of the group, and it's going to give me an invertible matrix. So GL just means the set of invertible matrices of size, dimension of B lambda. And how is this guy defined? Well, it's actually not too terribly hard to see or to think about this. If this is defined as e to the IA, this is simply going to be defined as the exponential. This is big add lambda, small add lambda of A. So let's take a step back, because this is at the heart of everything that we want to do. If you get this, you're good to go from here onward. So let me take a second to stay here and focus on these equations. So let me go all the way back to tell the story. We've identified the group that represents the action of our unitaries of interest. Then we say, well, we're interested in finding where can the, if I take an operator and I conjugate it via unitaries of the group, where can this go? And here we leverage representation theory to think about invariant subspaces. Because I know that if O belongs in one subspace, whenever I Heisenberg evolve it, it can only stay here. It cannot go anywhere else. So this is great, because now we can just study the action of our unitaries in here. We want to study how unitaries act in this irrep. And we said, well, the trick is, let's try to go to the algebra level, where conjugation of the group means commutation of the algebra. We literally studied how elements in the algebra commute with elements in our irrep. And this allowed us to define the adjoint representation, which now it takes a matrix, which was a generator in our circuit, 2 to the n times 2 to the n matrix, and we get a dimension B lambda times dimension B lambda matrix. So we've already done quite a big of a dimensionality reduction. Then we said, we know how the algebra acts via commutation with this adjoint representation. We use the exponential map, and we find that this is how the group acts in the algebra. Because more precisely, and this is what's actually super cool about this, is the following. That if I now want to know how this guy acts, and let me just assume that U is equal to the IA for simplicity for now. Well, turns out that I can study its action over a basis, because every O can be expanded in a basis of the module. So I can just first start with a basis of the irrep. And this is actually going to be given by this. So what's really cool about this equation, let me put this here. I'm missing a mu nu by A, mu nu, P nu lambda. So this is great, because now to know how our unitary acts on an element of the EREP, we just need to know this much smaller dimensional matrices, just extract their matrix entries, and they're going to tell us how this evolution occurs. So this is exactly what we wanted. We wanted to know how the unitary acted on the EREP, and we've managed to do that. We've explicitly written the action as an equality with objects that could be much easier to handle than just our exponentially large matrices. So this is an extremely powerful artifact. And the cool thing about this is that all these maps are linear. So if now you have something that looks like exponential of summation of things in the algebra, so let me just write it like this, k theta k, it's not hard to prove that the adjoint action is going to be like this. So this kind of satisfies all the properties that we wanted. Yeah, let me start there, and then we're going to head over here. Yes? The Lee closure. Yes, like this case. So, right. So this is very interesting, what you just said. Yes, if you want to continue your question, please. Yep. Yes. So, yeah, let me repeat the question, because I think that we didn't get the mic on time. The question was two-part, which was, what happens when this guy is isomorphic to SU, and it should not be SUN, it should be SU2 to the n. So the thing is that if that's the case, yeah, your system is what people in control literature call it's controllable or universal, meaning that you can map any state to any other state. And in that case, yes, your EREPs, but it depends on what space they're going to be acting on. They're irreducible over H, but not over B. So once you think about what is the size of the EREPs, that is only true whenever you're thinking about the action over H. Like something that is a one design or something that is irreducibly acting on a space, it's only irreducible here, but this might still have EREPs. And in fact, the Schur-Weyl duality tells you that this has two EREPs, the symmetric and anti-symmetric. Exactly. So that is true. And we will see in just a second why the case of this being SO2 to the n, SU2 to the n is not so interesting for us. This, for instance, is not a one design. So this ansatz is not even a one design because, yes, even on H, this is not a one design. It's not acting irreducibly on H. So that's going to be case by case dependent. So it's not necessary that it will act irreducibly. Yes, and we will talk more about Schur-Weyl duality tomorrow. But yeah, and I saw some question here, but actually let me take this.
I have a question here. A, in the second line of the last blackboard.
Yep.
A represents an element of the Lie group, right? O sea, the Lie algebra.
Yeah, I should remove the I if it's an element of the Lie algebra.
That was not the question, because A must be Hermitian in order to preserve the unitary of U, but...
it needs to be, in this case, Q-Hermitian. The elements of the algebra are skew-Hermitian and not Hermitian. So they're like a Hermitian matrix multiplied by an I. Whenever you conjugate, you get a minus sign.
Perfect. Anti-Hermitian then, or what? I didn't...
Skew-Hermitian.
Skew-Hermitian, yeah.
It means anti-Hermitian. So whenever you dagger them, you get a minus sign.
Minus.
Yes.
Excellent.
So
Thanks.
it's kind of unfortunate that in quantum mechanics we work with Hermitian generators because depending on the situation, I might or might not put an I. So yeah, this is just kind of like those gaps that we have with mathematics. I don't know if there was another question somewhere around here. Cool. So this is really great because we've exactly managed to solve the problem that we have. which was we wanted to know the action of our unitary in this subspace, in this EREP. Now, the question is, we can start asking, when is this going to be efficient? And let me see that if I'm forgetting anything. Okay, something that is worth mentioning. If your group is compact, this representation is faithful, which is kind of nice. If your group is not compact, you might have some two elements that get mapped into the same. But in general, for compact groups, this is going to be a faithful representation. So that means that for any element in the group, I will get one element in this much smaller representation. So actually, before getting into discussing how efficient this is going to be, remember that why are we doing all of this? Because we want to compute loss functions. We want to simulate loss functions. You're giving me a circuit, and I want to be able to use a classical computer to give you the expectation value of that L that is over there. So if we start with this L, and let me already do this, we already know how this guy right here acts. So I can just, first, I can take O, and I can decompose it into a linear combination of things in the EREP. And remember, I defined those Hermitian because I put an I here. So P's are Hermitian, so that means that I can decompose this in this way. For convenience, let me define this vector, which is going to be mu1 all the way to omega dimension b lambda. And I can rewrite this equation right here now as summation over mu, w mu, and use this equation right here. Do you want me to write this for all the product of unitaries? Let's actually do this correctly, yes. Let me do this correctly. So because of linearity, the other thing that is pretty nice is that if I now think that I have U1, U2 acting on P mu lambda, U2 dagger, U1 dagger, you can just use this equation twice. And in this case, you're going to get a summation over nu1 and nu2 of phi adjoint lambda of u1 mu nu1 phi adjoint lambda of u2 nu1 nu2 p nu2 lambda. So if you have a product of unitaries, the extension is trivial. You just do this multiple times because everything is linear and works really nicely. So let me, for now, just for simplicity, assume that this just contains a single unitary so that we don't have to get boggled up with all of these matrices multiplications, because that's not the point that I want to highlight right now. But we'll have something here, which is the summation over nu of the adjoint action in the lambdath module of my unitary entry mu nu, the trace of rho with p nu lambda. And what's kind of cool about this is that if I define now a vector E, which is just the trace of rho with p1 lambda, the trace of rho with p dimension of b lambda lambdath, and I can't really close this here. It's not really hard to convince yourself that this is just this guy. So it's literally just take a vector of dimension b lambda, multiply it by a unitary of dimension b lambda times b lambda, and the inner product with another vector E of dimension b lambda. Is it large enough that people can see from that side? Cool. So this is awesome, because now we're just working with objects that are of dimension b lambda. We don't need to work with exponentially large vectors anymore. And the question is, okay, how would we go about let's run through the whole pipeline. We've already identified the subspace. We've studied the action of the unitary in this subspace. Then we said that the final step is to determine what is the set of measurements that I need to do on my quantum state to be able to simulate this loss function. So with everything that is on the whiteboard, and I tell you what is the set of measurements that you would do to your input state during an initial data acquisition phase so that you could compute this loss function for any unitary in the group. What are those measurements that you need to do? And I can rewrite this equation right here because it's actually going to be the most important thing that we have. So let me get rid of BCH. And that way, it's central for everyone. And if you care to venture an answer, just go ahead while I write this. Exactly. You need to do homography of the state in the basis of the subspace that you're living in. That's exactly it. Let me just finish writing this up. Yes, that is all that you need to do. You need to measure the entries of this E vector, which, as you can see, is independent of the unitary. It just depends on the EREP that you lived in. So this is something that you can do during some initial data acquisition phase, which doesn't require information about your unitary. But of course, now we have to face the question, is this going to be efficient? Is all of this going to be efficient? Because if it's not, then your classical simulation is pretty much doomed. So how do we guarantee efficiency? Is it okay if I erase this? So let's review some of the results that we have before going into specific examples, which are, what is the size that the EREPs in B can have? And I actually erased this equation, which was important. I think it was here. So what is a necessary condition for this to be efficient? We said we now need to deal with matrices, unitaries, that are dimension B lambda. So the first thing that we would like is that the dimension of B lambda to be at most polynomially growing with n. Because if it isn't, if this is exponentially growing with n, we can't even construct these matrices because they're exponentially large. So we lose all potential efficiency. And not only that, we would have to do tomography on exponentially many objects, which violates our rule that we need to spend polynomial time during our initial data acquisition phase. So you can see that this is a necessary condition for you to have efficient classical simulability. Now, something else that we saw yesterday, and it's the first thing to remember, is that if I give you a group and you're thinking about EREPs, first of all, let's forget about trivial EREPs. They're not interesting because nothing happens in there. There is no information processing that happens in there, so who cares about trivial EREPs? So we'll think about non-trivial EREPs. And we already know from point number 1 that the smallest EREP that you can potentially have is that of the fundamental representation of your group. So if you find that the dynamical Lie group, G, is, for instance, a representation of something that looks like this, that would mean that the smallest one of these guys has to be exponentially large, because this, the fundamental representation, is just 2 to the n times 2 to the n matrices. So this is very bad. So a necessary condition for you to have this is that you need to have small groups. You cannot have exponentially large groups. If your group is exponential, it's not classically simulable. But then you might be like, aha, so to avoid classical simulability, let's go to exponentially large groups. But the problem is that we already know that exponentially large groups will have barren plateaus. And we can prove this rigorously. So you can see that kind of like the math is telling us that there's no free lunch. You kind of try to tackle it from one way, and it tells you no. You try to tackle it from another way, and it's just like you need to have small groups. So this is the basis of Lie algebraic simulations and how you would go about trying to dequantize some algorithm. This is all very abstract, so let's try to do now some specific example, because without examples, I think that it's going to be hard to understand this. And we said that we were going to be focusing on the transverse field Ising model problem. Am I forgetting something? Oh, actually, it's something that is a lot of fun, which you might actually be wondering is, we live in a polynomially small subspace. We have all of this. How can you guarantee that this is not going to have a barren plateau? How do we know that this is not going to have a barren plateau? Well, it turns out that if you do a little bit of calculations, you can try to ask the question, what is the variance when my unitaries are sampled over my group? I'm going to assume that this is uniform hard random sampling. So that means that unitaries are sampled uniformly from the group. If this doesn't make sense, tomorrow we're going to explain how to compute these guys. And I want to know how much does this concentrate, if this variance is exponentially small or not. Well, using all of this, and kind of like page number 5 of any book of representation theory, you can also get to a shamefully easy result to prove, which is that this variance is equal to this guy right here. And just to be formal, let me put a lambda here, because your state is going to have different projection in different lambdas. So we should definitely make it very explicit that this is just a representation in the lambdas module. This is the inner product. This is a number, right? I have a vector multiplied by another vector. This is a number. I do realize that there's something that I forgot, which I will do now, which is give you references for all of these things that I'm talking about. So if you want to learn more about structure constants, there's this paper right here from our summer school, which I'm already kind of advertising, and I'm going to talk more about this tomorrow. This was also heavily inspired from Rolando Soma's PhD thesis, which you can find here. It's always funny whenever you see that the links are quant.ph, because you kind of realize that they're not as new. If you want to learn more about basics of representation theory, I would recommend the whole book. It's called Lie Groups, Lie Algebras, and Reps. Well, and representations, right? It doesn't say reps, algebras, and reps. A little bit of self-advertisement. We also have a tutorial on representation theory from the optics of quantum machine learning, which is this paper right here. And I also wanted to give a reference for this equation. There's 2 papers that simultaneously prove this. One was from our group, the other one was a group in JP Morgan. And here you can find the proof of that equation. So let's stare at this for a second. What is this telling us? The first thing that we see is the dimension of the E-rep. This is really nice, because it's already telling us if you have an operator that lives in an exponentially large E-rep, it's what we said, it's the curse of dimensionality. It's explicitly stated here. But you can also see that we've seen how the measurement operator can affect you as well as the input state. So this guy right here is the projection of a state on some set of operators. You can think about some set of p's that are arising from the basis of the subspace. This doesn't have to be, this is not like standard purity. This is not a number that is upper bounded or lower bounded. It's upper bounded by 1, it's lower bounded by 0. You could find a bunch of operators that whenever you take the inner product with rho, you just get 0. So this guy right here could also be problematic. And this means that even if I have a polynomially large E-rep, I could have a state that has no component in that E-rep. And in our paper, we actually show that this is a true measure of quantumness or non-classicality or resourcefulness, if you know about resource theory, with respect to this group. So the math is also telling us that this notion of entanglement producing issues, kind of gets generalized to this algebraic sense. So I kind of really like this equation because it just formalizes all of these ideas that we have, which barren plateaus depend on what is your observable? Which subspace does it belong to? Is it exploring an exponentially large space? How much resourcefulness does your state have with respect to this subspace? So all of the things that we kind of like learn from the community, they're kind of just all condensed in this pretty equation. So how am I doing in time? We still have 20 minutes, which is perfect, because that's going to give us time to go into the Ising model. So if we remember the circuit, let me actually go back to show it. We had the first one right here. I'm going to do a slight change of basis for convenience, where I'm going to say that the ZZ gates are actually XX gates, and that the X rotations are Z rotations, because this aligns more with what people do in condensed matter, and you'll see the connection in condensed matter in just a second. So we said our set of generators is just I, and we had ZIs, union I, XI, XI plus 1, when I goes from 1 to n. And this is very reminiscent to this example that we did here. And once you do the Lie closure, I can explicitly give you all the operators that appear here. This is going to be the span over the real numbers of I ZIs. Of course, they have to be there. But then we also have these guys right here, union. I'm going to write stuff, and then I'm going to define it. Where whenever I write an operator of the form AI bj with a hat, this means that it's a Pauli A on the I side. Then I have Z's in the middle, Zi plus 1, Zi plus 2, Zj minus 1, bj. And you can actually show that this representation of an algebra is isomorphic, or G is actually SO to N. For people that know about Jordan-Wigner transformation, this is at the very heart of Jordan-Wigner transformation. This is the algebra that represents fermionic systems. And before going into why these are fermionic systems and how to understand them, I just want to emphasize that this is a very small algebra. It grows polynomially. The dimension of this algebra is 2n choose 2, which is order n squared. So it's polynomial. So this is great, because polynomial algebra will allow us to have polynomially sized E-reps. So why have I been mentioning like condensed matter, Jordan-Wigner, and whatnot? Because it turns out that if you define Majorana operators in this way, and if you hear Majorana operators, don't get scared. It's just Pauli's that I'm just going to be giving them a different name. So let me define 2n Majorana operators. C1 is just x1, so good so far. C2 is just y2. C3 is just z1, x1. C4 is just 2, y2, and I keep going until I get to 2cn, 2n minus 1, which is zn minus 1, xn, c2n, which is just z1, zn minus 1, yn. Pauli's, right? There's nothing funky about them thus far. Why do we call them Majorana operators? Well, because if you take Ci, Cj, and you look at their anti-commutation relationships, you get like delta ij. So they're a Clifford algebra, and they actually represent, in a very veritable way, Majorana operators for a fermionic system with n modes, where two fermions can occupy n modes. And this is at the very heart of Jordan-Wigner transformation. If you've seen Jordan-Wigner transformation, you will realize that this is the Jordan-Wigner transformation, because I can define creation and annihilation operators. For instance, I can define A1 like C1 plus C2. I think there's a square root of 2 somewhere here. I'm not sure about this square root of 2. But you can see that this is going to look like S plus. And then if I do like A2, this is going to look like Z1 S plus on 2. So these are at the basics of a Jordan-Wigner transformation. And this is why sometimes people refer to this circuit as free fermionic. To fully see this connection, it turns out that you can take this representation of the algebra, and you can write it as the span over the real numbers of the product of two distinct Majoranas. So this algebra, which looked kind of weird, is really nicely represented in terms of Majoranas. It's just take the product of two distinct Majoranas. You need to multiply by an I. No, you don't need to multiply by an I. An I makes them Hermitian. No I makes them skew Hermitian. And you will get this really nice algebra. If you write this in terms of creation and annihilation operators, this will be an algebra that is quadratic in creation and annihilation operators. And for people that know this, from here, I can get Hamiltonians that are quadratic in creation and annihilation operators, which, by exponentiation, is going to give me free fermionic evolutions. So this is why transverse field Ising model is also sometimes called like free fermionic circuits, linear optic circuits, match gate circuits. It's because of this connection with Majoranas. But now this is really nice, because you can use a little bit of rep theory. And under SO2N, this is going to decompose into blocks BK, where BK is the span of K distinct Majoranas. So you have B0, which is no Majoranas identity. B1, 1 Majoranas. B2, 2 Majoranas. And this means that the dimension of BK can actually be proven to be 2n choose K. So this is great, because we had a small algebra, which led to a group that whenever it's acting over operators, it has small E-reps. And we can do the simulation over those E-reps. So if we go back to original problem of the Ising model, we see this Hamiltonian, and we're like, well, we're doing VQE. We want to get the ground state of this Hamiltonian. So O is exactly that thing right there. So where does this guy belong? Almost tautologically, it belongs in the algebra. So that's product of two Majoranas. So that means that it belongs to B2. So if we want to do the simulation of this algorithm, we just need to focus on the B2 E-rep, which is of size 2n choose 2, so squared. It's polynomial. And we can do everything perfectly fine. So this is great. We can now simulate this VQE in this E-rep very efficiently. We just need to go through all the steps of constructing the adjoint action and doing all of this. I can give you a tip if you actually want to implement this. It's pretty nice. You can do simulations of Ising models in like 300 qubits in your laptop in a matter of seconds. So it's actually super efficient. So we said that we needed to compute something that looks like C mu, C nu. And I need to compute this, its commutator, its action on some modules. So I can actually give you the more general formula, C1 alpha K. So how does this one look inside of each E-rep? Because then you can construct the adjoint action in all the E-reps. Well, this is going to be equal to 0. Let me define the set S of indexes as nu1, alpha 1, alpha K. If mu and nu belongs to S, or if mu and nu don't belong to S. And it's going to give me plus minus 2, C mu, C alpha 1, C alpha I minus 1, C alpha I plus 1, C alpha K. If mu doesn't belong to the set, and nu equals to alpha I, and the other one should be pretty much symmetric, C nu, C alpha 1, C alpha I minus 1, C alpha I plus 1, C alpha k, if nu doesn't belong to the set, and mu is equal to alpha I. So with this is essentially all you need. Because getting this, in general, might be really hard. It's not trivial that getting the structural constants is going to be easy. In this case, it's simple, because we can write everything in terms of Majoranas, and the commutation and anti-commutation relationships of Majoranas are quite easy to get. So getting the structural constants is simple. We get the structural constants, we get the small adjoint representation, we get the big adjoint representation, and everything follows through. Also, something interesting to mention is that these expectation values, if you're trying to get them, you can get them via fermionic classical shadows. I think I have a reference here, which are shadows specifically based to get the expectation value of fermionic operators. In particular, just like classical shadows work for operators that have small bodiness in terms of Pauli's, these shadows will be efficient whenever you have small number of Majoranas. So you can see that this notion of locality kind of gets translated universally. References for fermionic shadows. A lot of these papers are published, but I kind of hate paywalls, so I always give archive references. So we kind of have gone through the whole pipeline. And I only have 5 minutes, so I think I should start trying to wrap up. Let me see if there's anything else that I want to say. OK, let me first show you results for simulation of the Ising model. Actually, why does this guy not work? Why will this have barren plateaus? Because if you do the Lie closure, which is the extension of this, you will show that the Lie algebra is isomorphic to SU 2 to the n, which is precisely the problem that this is going to have a barren plateau. And we can understand why adding some gates can significantly change the way that your algorithm works. So very quickly, no more pen and paper, no more cheat sheet. This is just a benchmark of what is the cost of doing this simulation. This was made on a single core in a student's laptop. So this is kind of like very, very simple single core benchmarking. And you can see that you can do up to 200 qubits in what is the time per gate, like 10 to the minus 2 seconds. This is how much memory is going to take you in megabytes to do a full state vector simulation of these expectation values for a free fermionic circuit. So this is super efficient. So we could, don't train VQE Ising model in Penny Lane. Do it via the algebraic simulations. Yeah. Something else that is interesting is that we can now use this for dynamical simulations of problems of interest. People that know about fermionic systems, they might be saying, oh, but you can always use Week's theorem. You can do simulation of fermionic systems very efficiently, get expectation values of a couple of Majoranas. But this is only true if your initial state is Gaussian. So if this means nothing to you, that's OK. If Week's theorem means something to you, then this is important, because Week's theorem is only valid for Gaussian states. Here, our initial states can be arbitrary. I can pick any initial state. It can have a lot of fermionic entanglement. It can have exponential fermionic extent, which would be exponentially expensive via Wick's theorem. But if you pick a small module, you can do some form of dynamical simulation and study of take a very non-Gaussian state and evolve it with a Gaussian unitary. So we've done this, this problem of simulating dynamical time evolution. This will be exponentially expensive via Wick's theorem. This is just to mention that some people say, like, oh, this is Wick's theorem. This is no. This is completely orthogonal. We're tackling something different. We can also do VQE on 50 qubits. And who here has heard about overparametrization in quantum neural networks? OK, there's a few subset of people. This is a really interesting result, where if you increase the number of layers, say that you have VQE on 50 qubits, and you start increasing the number of parameters that you have, eventually, and this is the probability of converging to the ground state, you're going to have very low probability, and then boom, phase transition. Computational complexity becomes very, very simple to optimize over. And the reason to understand this is this gives us the answer. these unitaries are exploring a Lie group. And we know that the maximum number of independent directions that a unitary can move in is a dimension of the Lie algebra, the tangent space at the unitary. So if you have a number of parameters which is equal to the dimension of the algebra, there might be more or less redundancy, so a bit order of dimension of the algebra, you're essentially parametrizing all possible directions in which your unitary can move. So here we can see that you can over-parameterize these circuits by about half of the dimension of the Lie algebra. So this is the number of parameters divided by the dimension of the Lie algebra. So this means that actually for most problems, you can get very efficient over-parameterization with this kind of circuits. Something else that I want to mention is you might be saying, well, you're kind of cheating because when are we going to have this? To have this, we need algebras that are small. Most algebras are exponentially large. So how come? What are the algebras that we know that are polynomially large and not exponentially large? It turns out that there's not many. There's actually, I think, the free fermionic ones, I'm going to group them in a family because you can have SO2n, UN, O2n, but they're all free fermionic algebras. Then you can also have permutation invariant circuits. If you have circuits that are invariant under permutation, so you take a circuit, you permute any set of qubits, the circuit should remain the same. That also has small Lie algebra, and that's about it. And you remember yesterday when I told you, oh, we managed to prove that by putting symmetries into a model, we got the holy grail of properties, no barren plateaus over parametrization, generalization. It was a permutation invariant circuit, which turns out to be classically simulable. There is a caveat that getting these guys could be as expensive as n to the sixth. We don't know. If anyone likes Schur-Weyl duality and wants to try to find efficient algorithms to compute structure constants for Sn, that is a really great problem that I'm very interested in. If you're interested about classification of dynamical Lie algebras, I'm just going to give you some references to see what the state of the art is. This has become all of a sudden a super interesting area of research. We're now just computing dynamical Lie algebras of circuit. Seem to be an interesting problem on its own. We recently, I think, last weekend for the QIP Rush, we put out a paper where we're studying dynamical Lie algebras for QAOA circuits. And there's quite a bit of work nowadays out there. And I think that that pretty much covers what I wanted to do, which is like 10:30 on the clock. And just for tomorrow, we're going to try to get that QCNN. Because we already know that this was all classically simulable. And with that, I'm happy to take any questions that you might have. Yeah. Well, it's still a unitary at the end of the day, so it still fits in this framework. You can have a branching unitary. So maybe let me take a step back. The question was, what happens if you have a branching unitary? Can you define branching unitary? Because I don't want to answer something that is maybe not what you have in mind. How do you define like a branching unitary? Right. What I can say is that unless you're doing super weird stuff, this is a pretty powerful framework that will capture a lot of things. You can try, for instance, there is this paper that says free fermionic circuits are not universal, so let's start doing like sampling circuits, putting other gates, and making them universal. And then they're really happy because they show that their circuits are now a design. For me, it's like, well, you've just kind of like shot yourself in the foot because now it's not going to be trainable. So I guess that the problem is that if you're trying to do stuff to veer away from classical simulability, the problem is that pretty much anything that you do is going to take you to something universal and is going to have a lot of issues. And just an important comment there. Why do you have this computational phase transition in the training of VQE here? Is because think about this. You have a unitary that is trying to move on dimension of the Lie algebra directions. If some of them are restricted, you're going to get fake local minima, which is there is some direction. I just cannot access it because I don't have the possibility to move in this direction. So a lot of times, local minima, they're not true local minima in the landscape in the sense that if you would have enough parameters, those local minima would disappear. And this is actually what happens. This is just spurious or fake local minima disappearing. So you might say, okay, let me take a circuit with an exponentially large algebra, so no classical simulation, but let me do it very shallow so that I don't get barren plateaus. Well, now you have exponentially many local minima because you have all of those directions that you can't explore. So yeah, now you can start to see why I get so flustered about variational methods.
So for my old school mind, like I would associate something that is easy to simulate with Clifford circuits, right? Like typically you would say, well, okay, if it's Clifford, we know how to simulate, and you need to put like some non-stabilizers inside the circuit to make it hard.
Yes.
So this seems somehow very different. How the two things are connected?
It's actually exactly the same.
Okay.
So Clifford is simulable because it's, where did I write the algebra of fermions? The SO2n, I don't know. Here. It's SP2n over the Z field. So it's actually very related. Like Cliffords are in a sense kind of like discretized bosons that you're transforming, and here you're transforming like fermions. So this can be promoted to a universal quantum circuit by introduction of non-Gaussian states or fermionic swaps, which are the equivalent of T-gates.
Okay.
So there is this nice paper by Richard Schosa and Andrew Zhao, where they show that with match-gate circuits, you can get universal quantum computation with injecting magic. So it's actually exactly the same thing.
Okay, perfect.
And something that I mentioned yesterday, which maybe I should mention now, is that there are elements in here which are completely global. There is here the element x1, a bunch of z's, xn, and that will be trainable. But for instance, if you're trying to train on this measurement operator, this belongs to B2, and this is trainable. But if you're trying to train on this, O equals x in the n/2 position, this belongs to B n/2, and this is completely untrainable. So this is an example where local observable in Pauli's is trainable, local observable in Pauli's is untrainable. But in Majoranas, this is local, 2 Majoranas. In Majoranas, this is highly non-local, n/2 Majoranas. So just be careful with these statements of what is global, what is local, because it depends on the setting at hand. Oh.
Thanks. So if I have local circuits, I will have like small, let's say, span of my extension, the extension of the of the algebra. The question is, you mentioned that you have the classical Lie groups, you have the symmetric group.
Yes.
Can you have a bright?
I don't know, because most of the groups that will appear for us are, they're the simplest Lie groups because they have to be compact because they're already matrix representations, right?
Yeah.
So because they're already matrix representations, that kind of like unitary matrix representations.
Yeah, because in my mind, I thought that only, well, if you have Majoranas, you will have also, can have UNs and SPNs. But
yes.
Which
you do have.
Yeah, well, but what wasn't expected is the permutation group that you mentioned that you can.
Yes.
So I thought perhaps if you have permutations, it's like easy to make like some kind of a small deformation to get a brighting. Do you?
I see what you mean. But here the permutations are not the group of unitaries, they're the symmetries of the unitaries. It's unitaries which commute with permutations.
Okay.
So
okay.
I'm not processing information via permutations, although you could. With there is a computational model of permutations. But here is the symmetries of the unitaries. So it's unitaries that commute with symmetries. They're not exactly permutations, the things that we're training.
And another small question is, in these models, the symmetries of the algebra of operators play any role? So, for example, in the AC model, you have Vanier duality, right?
Yeah.
So, can you at some point like trace back the role of the Vannier duality in the extension of your dynamical algebra?
I think you could. I haven't seen this done. But we kind of use this whenever you show that this guy is the algebra. We kind of get an explicit representation of the basis, the mapping. This is called the spinor representation and kind of touches bases on that. I haven't seen it explicitly worked out, but I'm certain that if you dig enough, it's kind of like hidden somewhere here.
Okay, thanks.
I also don't want to take more time of people's coffee, so I'm just happy to chat offline. Thank you again.